Every second, industrial plants around the world waste massive amounts of energy. Heat produced, paid for, and then simply lost. But what if the wasted heat could be captured, reused, and turned into profit? What if the energy leaving one process could power another without burning extra fuel? This is not science fiction. This is the hidden engineering system quietly saving billions in energy cost every year, the heat exchanger network. Modern industries consume enormous amounts of energy. A significant portion of this energy is lost every day as waste heat, escaping unused into the environment. A heat exchanger is a device that transfers thermal energy from a hot stream to a cold stream without mixing the fluids. But real industrial processes rarely use just one heat exchanger. They rely on entire networks, carefully designed systems connecting multiple hot and cold streams. Heat exchanger networks allow waste heat from one process to become useful energy for another. Efficient heat exchanger networks also mean fewer emissions and a smaller environmental footprint. Designing these networks requires careful analysis, balancing temperatures, heat loads, and economic performance. From refineries and power plants to food processing and chemical manufacturing, heat exchanger networks are everywhere. And now, let's take an example and know how to calculate pinch temperatures and minimum cooling and heating loads. Let's consider this hypothetical process. Here we have multiple hot streams that requires cooling and multiple cold streams that requires heating. However, each stream has its own heat exchanger. Our job is to design a network so we can reduce the heating loads to the minimum and the cooling loads to the minimum. First of all, we are going to identify each stream and tabulate inlet temperature, outlet temperature, and CP. So for example, the first stream in feed 1, it has an inlet temperature of 80 degrees Celsius, an output temperature of 140 degrees Celsius. Then this is a cold stream that requires heating. Its CP is 5 kJ per hour. We are going to do so for each one of these streams. Then we are going to get this table. We're going to give each stream a number. We're going to write which is a hot stream or a cold stream, tabulate its supply temperature, final temperature, and CP. In this particular example, it is given that the minimum temperature difference is 10 degrees Celsius. Now to design the heat exchanger network, we need to identify the pinch point, then to design the heat exchanger network. We have several methods to calculate the pinch point. We can use graphical method, we can use problem table method, and so on. In this video, we are going to illustrate the problem table method. And if you want other video illustrating the graphical method, composite curves, and so on, just let me know in the comment section. So as we said in this video, we are going to illustrate the problem table method, in which we are going to start by using the table that we have built before, and then we are going to shift the temperatures. Hot stream temperatures are shifted downward by delta T minimum over 2. So in this particular example, we have delta T minimum of 10 degrees, then delta T minimum over 2 is going to be 5 degrees. So all the hot stream temperatures are going to be decreased by 5 degrees. So for example, the first stream supply temperature is 180, the shifted temperature is going to be 175. The final temperature is 50, and the shifted final temperature is going to be 50 minus 5, which is 45. The cold streams are going to be shifted upward by delta T minimum over 2. So for example, stream number 4, which is a cold stream, the supply temperature is 80. We're going to add delta T minimum over 2. In this example, it is 10 over 2, which is 5. So 80 plus 5 is 85. And we are going to use the shifted supply temperature and shifted final temperature for each stream to draw the problem table method. To do so, you have to identify all the temperatures and neglect the repeated ones. And we're going to draw each line representing a temperature. We are going to start with 25, 30, 45, 85, and so on. Then we're going to represent each line. Drawing the streams is going to start from its supply temperature up to the final temperature. So the first hot stream is supplied at shifted temperature of 175 up to 45. The second one from 145 to 45, and so on. For simplicity, I'm going to write the CP values of each stream. Now for each region, we want to get the CP cold minus CP hot. So we are going to sum all the CP cold, then we are going to subtract the summation of the CP hot. In the first region, from 175 up to 145, we only have one hot stream. So the summation of the CP cold is going to be 0 minus 3, which is the summation of the hot streams, and we get minus 3. In the second zone, from 145 up to 85, we have 4 streams, 2 cold streams and 2 hot streams. We are going to get the summation of the CP of cold streams, which is going to be 3 plus 5, which is 8, minus the summation of the CP of hot streams, which is going to be 3 plus 1.5, which is 4.5. So 8 minus 4.5 is going to be 3.5. You can do so for each region, and you are going to get these values. Now we need to calculate the heat load in each interval. So in the first interval, we are going to multiply negative 3 by 175 minus 145, which is going to be negative 90. In the second zone, we are going to multiply 3.5 by 145 minus 85. This equals 210, and so on. Now, after calculating the heat load for each interval, we are going to draw hot stream, then represent each interval again, and we're going to start by 0. Then we are going to subtract each heat load from this initial value. So 0 minus 90 gives us 90. Then 90 minus 210 gives us minus 120. Then minus 120 minus 120 gives us 0, and so on. Now you need to recognize the minimum value, which is in this example equals negative 120. And we want to shift this value up to 0 so we can get the pinch point. To shift negative 120 to 0, we need to add 120, and we're going to add this value for each single heat load. So 0 plus 120 gives us 120, 90 plus 120 gives us 210, and so on. Now, the value corresponding to this 0 value is 85, so the pinch temperature is 85. We have hot pinch temperature and cold pinch temperature. So the hot pinch temperature is going to be this pinch temperature plus delta T minimum over 2. So it's going to equal, in this particular example, 85 plus 10 over 2, which gives us 90 degrees Celsius. And for cold stream, it is 85 minus delta T minimum over 2, which gives us 80 degrees Celsius. So now we have calculated the pinch temperature for the hot streams and for the cold streams, and we can start constructing our heat exchanger network. To design the heat exchanger network, first of all, you need to represent the pinch temperature line, which is 90 for the hot streams and represents 80 for the cold streams. Then you are going to draw the hot streams, then the cold streams. The temperature of this graph increases from right to left. So right is the minimum temperature and left is the maximum temperature. The pinch line splits this graph into two halves. The first section is above the pinch and the second section is below the pinch. Now the first hot stream is being cooled from 180 up to 50. The second one from 150 to 50. And the third one from 90 to 30. Make sure to represent each line with the corresponding temperatures. So the third line is going to be represented from 90 to 30. You can't represent this line in the above section. We're going to repeat this procedure for the cold streams. So you have 3 streams, the first one from 80 to 140, the second one from 20 up to 140, and the third one from 25 up to 80. Remember that the pinch temperature for the hot streams are 90 and the pinch temperature for the cold streams are 80. At the end of the heat exchanger network, we want the section above the pinch to use only hot utility. So we need to provide the hot streams with the cooling loads needed so they can achieve the desired temperature. And we can use the hot utility to give extra heat load for cold streams if needed. Remember that when you design a heat exchanger network, always start from the pinch and move to outside. Let's start by calculating the heat exchanger network in the above the pinch section. We are going to choose any two streams. However, it's better to pick a cold stream that has a higher CP than the hot stream. Now we are going to pick the first hot stream with the first cold stream. And we're going to calculate the heat load in the hot stream and the heat load in the cold stream. The golden rule is Cp delta T. So Q hot is going to be 3 multiplied by 180 minus 90 gives us 270, and the Q cold is going to be 5 multiplied by 140 minus 80, which gives us 300. So the hot stream will lose all the heat load and its temperature is going to be reduced from 180 up to 90. And the cold stream is going to get only 270 kilowatt. Now we need to know the final temperature of the cold stream. And as we said, we're going to keep the pinch temperature and calculate the other temperature. So we are going to write 270 equals 5 multiplied by T minus 80. This gives us 134. So the cold stream is going to be heated from 90 to 134, not up to 140. Now we have to choose another heat exchanger. But before proceeding, you need to make sure that the inlet temperature and the outlet temperatures has a delta T exceeding the delta T minimum. So in the right side for this heat exchanger, we have a hot stream that has 90 degrees Celsius and the cold stream that has 80 degrees Celsius. So delta T is 10. This equals the delta T minimum, so it is okay. And on the left side, we have a hot stream that has 180 degrees Celsius and the cold stream that has 134 degrees Celsius. The delta T exceeds 10 degrees, so this heat exchanger is correct. Now let's pick the second hot stream and the second cold stream. Then we calculate the Q cold and the Q hot. The Q hot is going to be 1.5 multiplied by 150 minus 90, which gives us 90 kilowatt. And the Q cold is going to be 3 multiplied by 140 minus 80, which gives us 180 kilowatts. So the hot stream is going to reach the desired temperature, and now we need to calculate the cold stream temperature. Again, we are going to keep the pinch temperature, so we are going to write 90 equals 3 multiplied by T minus 80, which gives us 110 degrees Celsius. Now both hot streams reach the required temperatures. The first stream is cooled from 180 up to 90, and the second stream is cooled from 150 up to 90. However, cold streams did not reach the temperature, so the cold stream needs additional heat from a hot utility to increase its temperature from 140 up to 134, and the second stream requires additional heat to decrease its temperature from 140 up to 110. Now we are going to put two heat exchangers between the cold streams and an external hot utility, and we're going to calculate the minimum heating loads, which is going to be 5 multiplied by 140 minus 134. This gives us 30 kilowatt for the first cold stream. For the second cold stream, it's going to be 3 multiplied by 140 minus 110, which gives us 90. By adding these two values, we get the minimum heating loads, which is 120 kilowatt. This is consistent with the value that we have got from the tabulated method. Now let's go to the other section, which is below the pinch. In this section, we need to let the cold streams reach their desired temperature. And we have an additional cold utility, so if the hot streams did not reach the intended temperatures, we can use the cold utility to reach the desired temperatures. So, below the pinch, we want the cold streams to get all the heat load needed. This means that when we pick up the streams, we prefer to pick a hot stream that has higher CP than the cold stream. In this example, we can pick the third hot stream with the third cold stream, and we put the heat exchanger. Now repeat the procedure. Calculate Q hot and Q cold. Q hot is going to be 2 multiplied by 90 minus 30, which gives us 120, and the Q cold is 0.5 multiplied by 80 minus 25, which gives us 27.5. Now, the cold stream reached the desired temperature, and now we need to calculate the outlet temperature of the hot stream. Remember that we are moving from the pinch to outside, so we are going to write the pinch temperature and calculate the other temperature. So it's going to be 27.5 equal 2 multiplied by 90 minus T, so we get the T, which is 76.25 degrees Celsius. Now we are going to choose two other streams, the first one and the second cold stream. Repeat the process, you will get the Q hot of 120 kilowatt and the Q cold is 180. So the hot stream will reach the desired temperature and we need to calculate the temperature of the cold stream. So we're going to write 120 equals 3 multiplied by 80 minus T, and you can get the temperature of the cold stream, which is 40. Now the cold stream did not reach 20, so we need to provide additional heat exchanger from the second cold stream up to the second hot stream. Remember that you need to double check the difference between the temperatures on both sides of heat exchanger. And you need to find that the hot stream's temperature minus the cold stream temperature is above the delta T minimum. Let's proceed. The third heat exchanger between the second hot stream and the second cold stream. The Q hot is going to be 1.5 multiplied by 90 minus 50, which is 60, and the Q cold is 1.5 multiplied by 90 minus 50, which is 60. So the heat load provided by the hot stream is the same as the heat load needed by the cold stream. So both of them reached the desired temperature. And now, only one hot stream did not reach the final temperature needed, which is the third stream. So we are going to use the cold utility to reach this temperature. And we're going to call this the minimum cooling utility. QC minimum is going to be 2 multiplied by 76.25 minus 30, which gives us 92.5 kilowatts. Again, this is consistent with the first value that we have calculated in the tabulated method. So the final heat exchanger network is going to look like this, showing all the heat exchanger and the temperatures of the inlet and outlet sides of each heat exchanger, and we have calculated the Q heating minimum and the Q cooling minimum. Now I hope that you can calculate the pinch temperatures and design heat exchanger network for any process. Thank you so much and see you in the next one. Goodbye.